slide on here that took an hour and a half to animate. Let's see if you can figure out which one that is later. So what I'm going to do is I'm going to post this Zoom session as a video, and then I'll make a more refined version that just more or less talks about the key points as we go through. Okay, so let's get into it. Remember, Lewis structures, they're back. What we're going to be doing today is analyzing Lewis structures and assigning charges to them, something called formal charge. And here on these drawings, most of the atoms are neutral that are depicted on here. The only exceptions are, you'll notice that on this oxygen here and this oxygen here, they both have this negative sign in front of them. What does that mean? Let's talk about it. So in order to do this, let's look at a molecule called phosgene, COCl2. There are actually two appropriate ways that we can draw a Lewis structure for this. One way looks like this, where we have everything has its octet filled up. So this is a good structure. You'll notice here that we've got a double bond right there and a single bond on this chlorine. The other possible way that we could draw it is like this. So pretty similar idea. The only difference in this case is that now we put a single bond on oxygen and a double bond on chlorine. So what we're going to do is talk about, and both of these are viable Lewis structures. You're not going to be expected to, if we have something like this, choose which one's better, but I do want to talk about how we can evaluate it, and we'll talk about which one is better. So enter this concept of formal charge. Formal charge is a bookkeeping system that describes where positive and negative charges are on a molecule. And the formula for formal charge is as follows. It's equal to the number of valence electrons, aka the group number of a given element, minus the number of non-bonded electrons. So the non-bonded electrons are the electrons in lone pairs. Each lone pair has two non-bonded electrons in it. And the number of bonds. So the way that I like to think about this is, again, the number of valence electrons on an atom is its group number. The non-bonded electrons, the number of bonds, is basically, when you look at the Lewis structure, how many electrons are drawn in on that structure, assuming that each bond evenly shares its electrons. So what I mean by that is, if we look at, say, this bond right here. Every bond has how many electrons in it? A single bond has how many electrons? Excellent, good. So every bond has 2 electrons in it. So what we assume here is that these 2 electrons are shared evenly. So 1 on each atom. Whereas on the double bonds consist of how many electrons? Excellent, so good. So double bonds consist of 4 electrons. We assume that 2 of the electrons are going to the carbon and 2 are going to the chlorine. So it makes more sense when you do it. So let's actually do the calculations for these. All right, so we're going to calculate the formal charge on each of the highlighted atoms. So the chlorine and oxygen on the first one, the chlorine and the oxygen on the second. And I'm going to call the one on the left molecule A and the one on the right molecule B. So let's get into it. Here is our equation. The number of valence electrons minus the number of non-bonded electrons plus the number of bonds is our formal charge. So up first, we're going to do this atom, the chlorine on molecule A. So chlorine is in group 7. So that means that it has 7 valence electrons. The number of non-bonded electrons. Okay. So it's got 1, 2, 3 lone pairs on it. Each lone pair has 2 electrons. So the number of non-bonded electrons is 6. And then the number of bonds, it's got the 1 bond right here. So it's going to be 7 minus 6 plus 1, which ends up giving us 0. And we'll see most of the time atoms have formal charges of 0. Now then, we're going to do the chlorine on molecule B. So now we're going to focus and shift our attention over to this chlorine. Okay, chlorine, by virtue of being chlorine, is in group 7. So it has 7 valence electrons. But now notice there's a slight difference because in this case, the chlorine has only 2 lone pairs drawn in on it. And it has a double bond. So it's going to be 7 minus the 4 non-bonded electrons. And the double bond is going to count as 2 for the number of bonds, which gives us a value of positive 1. Now then, back to molecule A. And we're going to look at this oxygen. So oxygen is in group 6. So it has 6 valence electrons. And there are 2 lone pairs and a double bond. So it's going to be minus 4 plus 2, which gives us 0. So then that leaves us with one more, which is this oxygen right here. This oxygen, well, like any oxygen, is in group 6 minus, and it's got 6 non-bonded electrons and 1 bond, which gives us -1. And so I'm going to clear off all these annotations here just to make this a little bit less cluttered. The way that we can signify these formal charges is if an atom doesn't have a formal charge, you don't need to do anything with it. You don't need to write 0 because it's just assumed that it has a formal charge of 0 unless otherwise noted. Otherwise, all you have to do is write the charge right next to the atom. So that one's -1, and this one, this chlorine up here is +1. So which structure is better? If we were to evaluate these, if you were trying to figure out which one is the more pristine of the Lewis structures, generally speaking, we usually try to minimize formal charges. Formal charges of 0 across the board is generally more stable. Again, you're not going to be responsible for evaluating that, but if you were to be able to draw multiple Lewis structures, and this kind of agrees nicely with our rules of valence that we talked about way back in the day, roughly a month ago, where halogens like to make 1 bond, oxygen likes to make 2 bonds, carbon likes to make 4 bonds, nitrogen likes to make 3 bonds, etc. So really, it's part of that story. Another thing that I want to note is that if you add together all the formal charges on a molecule, you'll end up getting the overall charge on the molecule. So let's just write those in here. So on molecule A, every single atom has a formal charge of 0. So it's 0 plus 0 plus 0 plus 0 equals 0. Neat. On molecule B, it's the same general formula. Now in this case, we have 2 atoms that have 0 formal charge. We have one that has a -1 formal charge. And we have a +1 as well. But again, all the formal charges add up to 0 because it's a neutral molecule. Are there any questions about that? Okay, so what we're gonna do now is get some practice in on calculating these. So we'll do clicker questions here. And by clicker questions, I just mean we're gonna look at the 4 molecules on the next page, and I just want you to take a moment and calculate the formal charge on the pointed atoms. Don't type it into the chat until we go through it as a group, just so that everybody's a chance to challenge their formal charge prowess. So let's get to it. So what we're gonna do here is these are our choices. -2, -1, 0, +1, and +2. So up first, we're going to do this molecule right here. Specifically, we're looking at the oxygen that we're pointing at. So take a moment and see if you can calculate the formal charge on it. We'll give this about a minute or so. And when you're ready, just let me know, and we'll go through it. So take a moment. Again, don't write your answer yet in the chat. And if you have any questions about it, please let me know. Okay. Let's go, or I guess what we'll do for the first one, just so I can have an idea of the pacing, is when you're ready, just type in ready into the chat. Good, good. Okay, let's get to it. So, what do we think? Which option is it? Awesome, exactly. So, it's going to be 6. Oxygen is in group 6, so 6 valence electrons minus, there are 4 non-bonded electrons and 2 bonds on it, which gives us a formal charge of 0. Excellent work. Okay, so that's molecule number 1. Up next, let's do this one. Up next, let's do this molecule. So take a moment. When you've done the calculation, let's do the same system. When you've done the calculation, type in ready. Okay, what do we think? Awesome, well done. So it is indeed choice B. So oxygen, again, is group 6. And we have 6 non-bonded electrons and 1 bond, which equals -1. Okay, but wait, there's more. Up next, we're going to do this one. Just going to draw a different, these are basically going to be like Lucky Charms. We have a star. We're going to do the one with the crescent moon now next. So we'll give it about 30 seconds. Okay, we'll give another 15 seconds or so. All right, what are our thoughts? Good. Once again, we're looking at choice C, 0. So nitrogen, it's in group 5. So then we'll subtract from that. There are 2 non-bonded electrons and 3 bonds, which gives us a grand total of 0. And typically speaking, if something is making the number of bonds that its rules of valence dictate, like nitrogen making 3, usually it's going to have a formal charge of 0. Okay, which leaves us with one more. And we can use process elimination, but I'm on this kick of drawing Lucky Charms symbols. So the last one we're going to do is going to be, let's go with a clover. Let's make that clover green. It's a terrible clover, but gets the job done. So take a moment. Okay, looks like we're about ready. So what are our thoughts here? Excellent, it is choice D. So nitrogen is group 5. And from that, we're going to subtract, there are 0 non-bonding electrons and 4 bonds, which gives us a total of positive 1. Awesome job. Does anybody have any questions about that? Okay, so now let's talk about some applications of this. We actually just created one of the most important reactions in chemistry and in life, the molecules that are involved here. So we'll talk more about this at probably at some point next week. But this is actually a class of acid-base reaction. It's the simplest genre of reaction because all that's happening is a proton, a hydrogen, is moving from one molecule to another. So what happens here is as follows. This lone pair of electrons reaches out. And basically, I like to think of it as almost like one of those crane games. It reaches out and grabs onto the hydrogen and then pulls it over to the nitrogen. And the products that we end up getting for this are this molecule here, which is called acetate, which, as you just told me, has a -1 formal charge. And then we get this molecule that's called ammonium. And again, we'll talk more about this next week, but formal charges will help us kind of understand what happens if a hydrogen moves from one molecule to another. And something that I want to note here, a convention, is that this way that I have the molecule drawn here, it's equivalent to putting a -1 next to that oxygen. So there are 2 different ways that you can denote formal charge. You can either write the value directly next to the atom, or I think this is the more aesthetically pleasing way. You can just write a negative sign and a circle around it. That means -1. Likewise, a positive with a circle around it just means +1. And we're not going to be looking at any molecules that have atoms that have formal charges other than +1, 0, or -1. They are out there, but they're not as common. Okay. And yes, so what we're seeing here is a nitrogen that has 4 bonds, and that's okay. As long as it doesn't violate the octet rule, that's perfectly fine. So nitrogen typically makes 3 bonds, but if this hydrogen moves over to the nitrogen, it still has the octet rule, because if we look at our nitrogen, it's got 4 bonds on it. Each bond has 2 electrons, so it still has 8 total electrons. It just turns out it's a little bit more reactive than a run-of-the-mill nitrogen, but this is perfectly fine, it having 4 bonds. It can't have a 5th one, because then, whew, if it has a 5th bond, then that's 10 electrons, and no, we're not violating the octet rule. That's just crazy talk. Any other questions about this?
不需要时间吗？我随时我现在该找了。他几点考试？
Okay. So now let's talk about one of the oldest known reactions to humankind. I was reading a little bit about its history last night, and an account from the New York Times said that they think the earliest account of this reaction is that there were tribes of people, that there was a rainstorm and water collected a bunch of fat and ash. I'm not sure what type of fat, probably animal fat, some variety, and ran it into a river. They then noticed that in this river, it had the ability to make things get really clean. Like there was a patch of it that had these sudsy bubbles in it that would magically clean things. Enter saponification. So ash commonly has or potash commonly has a molecule called hydroxide, OH-. We talked a little bit about it when we talked about bases, but basically what happens is if you take any type of fat, so we talked about how fats have this glycerol anchor to them, and then have these really long hydrocarbon chains. It turns out if you take fat, and it could be, say, olive oil, it could be butter, it could be, you can extract oils from coffee, for example, and you treat it with a strong base, you'll end up making soap. A lot of people do this. If you do it, just be careful because strong bases are caustic, but you can make your own soap by treating oils, fats, etc. with hydroxide. And what we end up creating when we do that is we end up turning this one molecule with the 3 long chains into 3 smaller molecules, each with a long chain and each with an oxygen that has a negative formal charge on it. So why is that significant? What makes soap do what it does? Oh, the other thing that we get from this reaction is we basically we cleave these off of the glycerol backbone. So the other byproduct is this molecule over here, which is called glycerol. Okay, so what makes this significant? Why is it notable that we have these long hydrocarbon chains with a charge on one end? Presenting the anatomy of a soap molecule. A soap molecule consists of a charged polar head. We say that it's hydrophilic. Hydrophilic literally means water-loving. Because, as we discussed before when we did the like dissolves like rule, things with charges, things with polarity, they really like interacting with water. But do long hydrocarbon chains like interacting with water? Nay, they do not. So we basically have this almost oxymoron of a molecule. We have one side that really likes interacting with water. We have one side that really doesn't like interacting with water. So we have the hydrophilic end, which will maximize interactions with water. And then these long hydrophobic tails will try to minimize their interactions with water. So how can they do that? If you have a bunch of these molecules together, how can it become most favorable? Well, what our goal is going to be to make the charged side able to interact with water and to have the uncharged hydrocarbon chain burrow away from the water. And this manifests itself in a number of different motifs. We looked at things called liposomes and micelles and bilayers. So let's talk about the micelle, which is what soap does. The way that this manifests itself in living systems and in water is the water will swarm around that end, and then our nonpolar end will burrow away. So it doesn't make much sense. It can't really burrow if there's only one of them. But if we have a lot of these molecules together, this is what they end up doing. So here we have a whole bunch of these soaps together. They will spontaneously form what's called a micelle. So assemble, 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 and voila. What we get is this sort of motif, where you'll notice that on the outside, we have the charges able to interact readily with water. So we're assuming that water is swarmed around this structure here. But in the middle, we have this core of hydrocarbon chains that are maximizing their interactions with each other, which is, what hydrocarbon chains like to do. And it has the added benefit of keeping it away from the water. So the water's on the outside, and then we have this core of hydrocarbon chains. And that is what makes soap do its thing. So what happens with this if this micelle interacts with, say, a pathogen, a bacteria, or a virus? Let's talk about it. So first, in water, for soap to work, if you put soap on your hands and you don't have any water, you just end up with this greasiness that doesn't really, it just kind of plopped on there. It requires water in order to get it to do its thing. So, a review of membranes. Cells are surrounded by chemicals that have basically this motif. They have a charged side that's hydrophilic, and they have an uncharged side that's hydrophobic and wants to get away from water. So this is a recycled slide that we did the week before spring break. And this like dissolves like principle tells us why these motifs will spontaneously form. So we have a polar end and we have a non-polar tail that will help us kind of draw a cartoon that depicts this. So these lipids with the charged ends can form micelles, where there's one layer of charged things on the outside and then the core. They can also form these things called bilayer sheets, which yeah, there we go. Where again, what they're doing is they're arranging themselves so that the charged end can interact with water. And the uncharged ends don't. They burrow into this core and they interact with each other. So this sort of bilayer is what surrounds the cells in our bodies. It's also used in viruses that have envelopes to them. So let's talk about the anatomy of a virus. So viruses have a number of different morphologies to them. I figured that the most relevant one to talk about would be talking about the anatomy of a coronavirus. So this is basically what it looks like. It has the genetic material in its core. in this case RNA, it's surrounded by a protein capsid that basically acts as a way of sort of protecting the genetic material. And then around it, it has this lipid bilayer. And that lipid bilayer is what soap exploits to destroy the bacteria. Now, specifically, one of the things that's notable about this particular virus is they have these things called spike proteins. These spike proteins, we talked a little bit about what proteins are. They've got these amides that bond together, these monomeric units. What these do is it allows them to latch onto a tissue so that it can then fuse and insert its genetic material. So how does soap protect us from these? This is a video of soap in action. Let's see what it does. So we have our virus down there. We have our, I didn't draw them out as a micelle, but these molecules of soap, they basically go in and they act as a chemical crowbar. So they go in, they interact with the lipid tails of the envelope and they pry them out. They form the micelle around it. And then because of the water that you're using when washing, it carries all of these away. Let's see that again. Whoop-pow! Whoosh! With its protective barrier gone, the virus will often go away with the water. And this took an hour and a half to make. Things you do in social isolation. Anyway, I'm really proud of that animation. That's how soap works. And that concludes today's lecture. So, thank you all for your time. I hope you all have a wonderful weekend. And I look forward to seeing you all next week. So please feel free to stick around. Let me know if you have any questions. I'll be posting a more refined version. Well, I'll be posting this along with the my talking. Well, both videos will have my talking, sorry. But I'll be posting this Zoom session for reference now, and I'll be posting a more succinct version that you can utilize later. Also later this afternoon, I'll post up a lecture assessment where you can go through and answer some questions. So thank you all for your time and have an awesome day/weekend.
Somebody mentioned in the chat that one of the assessment isn't up yet.
Right. Yep.
Okay.
So as I said in an announcement earlier, I'm going to post it later this afternoon, and I'll be giving an extension to it since it's not available yet. So I'll send an announcement when it's ready. My guess is I have to do another class and a meeting that'll probably get out around 5 or so. So my hope is to have it posted sometime between 5 o'clock and 6 o'clock.
All right, thanks.
And thank you, everybody. I hope that you have a great weekend as well. And for the lecture assessments, so I'm not going to physically change the score on it, but a 6 out of 7 will count as a 100%. So you only need half the available points to get full credit for it. So in effect, yes, a 6 out of 7 is a 100. Certainly.
It's a good animation.
Thank you.
So then, like, that effectively